Okay, so a way to graphically represent the isotopes is using an instrument called a mass spectrometer, and it actually shows an output of the different abundances and how many isotopes there are. So when you're looking at a graph like this, this indicates that there are 2 isotopes of copper. That's what that's showing us here. And then if you go over, it's telling us the percentage is another way of saying the abundance that we looked at before. So if I asked you which one is more common, you would say that the copper 63 is more common because it has a higher abundance. See? And to me, sometimes these are hard to read. Like if you go over to see exactly what percent that is, so that's, you just have to make sure they add up to 100. So let's look at a problem dealing with this, like something you'd see on the AP exam. So this would be a multiple choice question. It was one actually. So mass spectroscopy, here's the mass spectrum of Y. And by the way, in our POGL, we'll go into more detail of what mass spectroscopy is and how does it work inside the actual machine. But right now, we want to look at the data output and see what that tells us. So first thing I want to show you is we talked about the peaks. The number of peaks is indicating how many isotopes we have. So count how many isotopes this element has. We have 1, 2, 3, 4, 5, 6, 7. So you have 7 isotopes. So let's look at the question here. It says, based on the mass spectrum of atom Y, which of the following statements is false? So we want to make sure we're looking for the false statement. So we just counted there are 7 isotopes, so B is out. Peak A and D come from atoms that have the same number of electrons. Well, these are all from atom Y, and they're not ions, so they're all going to have the same number of electrons anyway. What else are they all going to have the same number of? Well, if it's atom Y, and we know it's all the same element, they should also have the same number of protons. So if we look at this, peak D comes from an atom with 4 more protons. That doesn't make sense either, because they're all the same. Same number I'm going to put here. So that's false. Peak C comes from the most abundant isotope in atom Y, and that makes sense because it's the highest peak there. Which one looks like it's the lowest peak? Well, to me, the one at 94 and 97 and 100 look like they're about the same. So I'd have to say that these guys are tied. Okay, here's another thing they could ask you. Instead of just asking you to look at the graph, they could ask you to identify who compound Y is. So if you remember, this is where it comes into play where we have to do the actual calculation. So I'm going to push this up a little bit so we have a little room here. But remember, it's average atomic mass is equal to, and we're going to go through and put the mass. So we have 92 times the abundance, but we're going to make that a percent. And I have this as about 15%, so 0.15, because it's hard to tell. Plus the next one, we're going to have 94. And if you want, you can pause this and see if you can do it yourself and get the right answer. Because again, it's interesting to see what you guys read as far as here. Obviously, this guy's 10, so we're going to multiply times 0.10 plus, and at the end, you need to make sure you add up that you have 7 of these. Okay, and the next one looks like it's also about 15, so I have 95 times 0.15 plus, and then the next one is 96, is also at 0.15. What do I have? 1, 2, 3, 4, 1, 2, 3, 4. So we're now at 97. So 97 times, that one looks like it's like, that's at 0.1 or 10%. Plus 99. This is annoying because it goes on 2 lines, but whatever. And that is a tough call, but 99 I'm going to say as at 0.25. And then I still have the last one, which is the mass of 100 times 0.10. So when I calculate all that, I end up getting that the average atomic mass is 96.3. So then when I go and I look at my choices, so 96.3, so I have to look at zirconium, which by the way is ZR, molybdenum is MO, and mercurium is AM, and einsteinium is EN. Oh, actually is ES. That's one that I do not use very much. So let's see on the periodic table here if we can find him. Oh yeah, Einsteinium's ES, sorry. Okay, so Einsteinium's mass is 252. So that's, no, that's not it. The zirconium, what is ZR? ZR is over here. ZR is 91.2. So I'll put that there. Molybdenum, MO, is 95.9. And americurium, AM, where is that guy? Down here, 243. So I know for sure C and D are out when I get down to that. If I look at this, C and D are out of the picture. And if I actually calculate based on that, it looks like my mass is the 96.3, which would be B. Again, that's me looking at the chart we have here. So let's continue on. Okay, another question they could ask you, which peak comes from an atom with the greatest number of neutrons? So remember, greatest number of neutrons, that is the difference. An isotopes have different number of neutrons. So the difference number of neutrons is going to be the one with the highest mass, right? The highest mass that we have here. So the one that has the highest mass is who? Not the percent abundance, the highest mass. So the one that's 100 here, which is in this case D. Okay. And that is that. The last slide that I want to show you, well, one of the last slides, I don't know which order this is in actually. So I want to talk about the application of mass spectroscopy. So if you look at these pictures here, there's some hazardous waste here. There's some firefighters working on a building. And this is a printout of a drug test. So I have a friend that's a firefighter, and we talk about how actually on their fire trucks, they have mass spectrometers because sometimes they need to figure out what an unknown substance is. One time he said that they were on the truck and there was a chemical spill of containers, something like this, and it was all over the road. And so they picked up a little bit of the substance and they put it in the mass spectrometer to see what it is. But before they got the readout, one of the crazy firefighters put his finger in it after smelling it and ate it. And my friend looked at him and was like, "What are you doing?" And he goes, "Oh, it's coconut oil." And sure enough, the mass spectrometer came back as it being coconut oil. Still not a smart decision on his part, but they were able to see what it was spilled on the road. In another situation like the one here, the fire, sometimes they want to try to figure out, was an accelerant used in a fire, and they can analyze substances, that are found in the house to see if that was actually used. When you get a drug test, the readout looks something more like this. You get these peaks, just like we've been looking at, and from those peaks, we can tell which type of drug is in the system. Something I think is super interesting about this is these are all metabolites. For example, if you were to do cocaine in your blood, you wouldn't find cocaine, you'd find benzoyladenine, which is a cocaine metabolite. It's after the cocaine breaks down a little bit, that's what's left. And same thing with heroin, like you never find straight heroin in the blood, you're going to have some sort of metabolite. So it's just a cool application of mass spectroscopy. All right, so we're going to move on to the POGL now, and that's our last thing.